So today we're going to be dealing with binary numbers. That's the major objective today. You're going to figure out how binary numbers work. And you should have your paper and a pencil. You should have your Flippy-do in your hand, and we're going to get into your Flippy-do. It says Flippy-do on it. And there's an activity guide that you're going to have in there, and you're going to have some activities to do when this is done. And I'll take out the hide piece, and let's take a look at this particular lesson. Now, when we played with binary numbers last class, we realized that one place value has two possible patterns, right? And if you remember, we used circle and we used a square. We had cut them out of those worksheets. Mine are red and blue because we're working in color, but yours were black and white. It's circles and squares, all right? Now, you had two place values, all right? It's one of the key things to understand. But now, what if I wanted to add a place value to it, all right? I can come up with four possible patterns, right? I could have, before the circle, I could have circle, circle, and then I could have circle, square. And then I could start with a square, and I could have square, circle, square, square. So I have 1, 2, 3, 4 possible outcomes right there. What if I went to three place values, right? When I went to three place values, I take the ones that are already did, and I could double them, all right? Because I have this with either circles in front of it or squares in front of it. In other words, I go from, all right, two place values, which gives me four possible patterns, right? To three place values, which gives me 8 possible patterns. Circle, 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 square. Circle, square, circle, circle, square, square. And I do the same thing with that. We get 1, 2, 3, 4, 5, 6, 7, 8. Other thing I'm going to tell you about this is we actually can map them to a numbered list. And I want you to look at this numbered list because this is going to be really important in computer land, okay? When we count, when we make lists, when we come up with index numbers, which you'll hear about later on, any of those in counting in computer land, you're going to be living with counting starting at 0. The value in a list, the first value in a list is going to be 0. 99.9% of the time, that's going to happen. All right, get used to that idea. Now, lists start with 0. Computer scientists, which you are, like starting at 0. Maybe you don't like it yet, but you'll learn to. All right, so what if, pretend for a second, take a minute. What if instead of 2 shapes, I had 10 shapes? What if I had 10 shapes to work with? For example, let's get 10 shape patterns. This is what we already have. Remember, computer scientists like starting at 0, right? That's because these are just shapes. That's what we have in American, British, European backgrounds. That's how we write the numbers. A lot of Latin-based languages do that. Other languages may use others. Remember Roman numerals? Remember when we express things with dice and we express things with clouds and we express things with other systems, other numbers, shape systems? These are just shapes. They're just the common shapes that are used pretty much around the globe for these numbers, but they're just shapes, all right? So if I want to do 100 two-shape patterns, I'm going to list this 10 times, all right? And then I'm just going to put zeros in front of the first ones, and then ones, and then 2s, and 3s, all the way down. And look what I have, from 0 to 99. That's 100 shapes. It's just not 1 to 100. It's 0 to 99 is how it works in computer land. So because of the decimal, if I have 10 times 10, I get 100 shape patterns. All right, that's because I went 10 squared, right? So if we're thinking about that, what comes after 0, 9, 9? Well, this is going to become a 0, and this is going to become a 0, and this is going to turn into a 1. So hopefully, you came up with 100. And then 101, 102, 103, 104. I'm just adding a place value. And I go from 100 times 10 goes to 1,000. And where is this heading? Well, it's heading for binary. That's one of the things it's heading for. Now, binary is simply a number system with 2 shapes. It's all I have is 2 shapes. I use 0 and 1 instead of square and circle, but that's all I have. 0 and 1 is all this uses, 2 shapes, binary. So when I make organized lists, I do counting in binary. If you notice, I even put that on my class pass thing where I said it's as easy as 1, 2, 3. That's because this is how you count binary, right? Now, in the binary, with each place value, you really only have, once you get to the third place value, you only have 7 possibilities, all right? So this value, 3 place values, are 0. Then once I add the 1, it's now valued 1. Once I add the 1 here, it's 0, 1, 0 is actually the value of 2. 0, 1, 1 is the value of 3. 1, 0, 0 is the value of 4, etc., etc. So what you're going to do now is you're going to make your flippy do. And your flippy do, you're going to fill it out, and here's your example. That's exactly how you're going to do it, all right? I want you to have that, and I want you to also take your scissors and cut it according to that cut right there. Just these little slits right here, all right? Understand that you're going to make these slits. Do not cut across this axis right here. I almost wish they had put the dots there. You're going to cut the sides, and then they're going to flip along here. And on the back side, you're going to put 1s. So all these numbers across the top, which is 2 to the 0, which is 1, 2 to the first, which is 2, 2 squared, which is 4, 2 cubed, which is 8, 2 to the fourth, which is 16, 2 to the fifth, which is 32. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, etc., 2 to the sixth and 2 to the seventh. Just so you know, you can pause and do that. I'll come back to it. But each place value represents 1 bit. So it's saying that each of these is a bit. There's a bit, right? And when you put 8 of them together, it makes a byte. And that's how it works, by the way. A binary digit, and they come in sets of 8. A binary digit is a nickname, bit. And each 8 of them put together is called a byte. A megabyte is 1,024 of this. All right? And then a gigabyte is 1,024 megabytes. It's this squared, etc. That's why they get larger. Now, you're going to try out your flippy do. I want you to take a second and, with your flippy do, represent these decimal numbers in binary. So you're going to take the flippy do, use your 1s and 0s, flipping them back and forth, and represent the decimal number 7. And then also represent the decimal number 20. All right? Take a minute, pause the video, and do that. I'll have you just pause the video physically. Hopefully you've done that, and if you've done that, the answer you should get should be that. Then do it the other way. Playing around with these numbers, build this with your flippy do right here. Build this number with your flippy do, and then build this number with your flippy do, and tell me what they are in decimal form, all right? The thing we know as regular numbers, decimal form. And hopefully, you came up with what we know is the value of 18 and the value of 31, expressed in decimal as 1/8 and 3/1. Now you've got this activity guide, and I'm going to get out of this for a second to kind of go over it, but what you've got for part 1, let me just pop out of this for a second. I'll go right over to the flippy do guide, all right? So the first thing you're going to do is you're going to do the 4-bit numbers. You're going to put them all in here. You're going to run this all out. 0, 1, 2, 3, 4, 5, 6, and 7. I want you to run it all the way out, all right? And then just run it out all the way out. And you can run it out way past through this, okay? What do you notice when you compare odd numbers with even numbers? You're going to see a pattern. And there is a pattern in that, all right? And then I want you to, with this one, find the chart, complete this chart with binary numbers that have exactly 1, 1. So you have a full byte here, right? 8 to 8 place of values. And then there's a series of numbers that have exactly 1, 1. They're all zeros except for 1, 1. Which ones are those? We know that 1 has only 1, 1. We know that 2 has only 1, 1. What's the next one that has only 1, 1? All right? Then find the equivalent binary or decimal numbers below. So here's the binary 100. What is that in decimal? All right? And use your flippy do as a resource. Here, it's the opposite. Well, the opposite process. You have a decimal, 5, the value of 5. In decimal, express it in binary. Use your flippy do. And then when you add the 0 to the right of a decimal number, it multiplies its value by 10, right? 15 becomes 150, all right? What results when you have the value, if the value of a binary number, you add a 0 to the right? For example, what if 1, 1 becomes 1, 1, 0? What happens in binary when that happens? Is this not the same as in decimal? In decimal, it goes up by a value of 10. I wonder what happens in binary. Now, look at this, 0, 0, 1, 1, and then 0, 0, 0, 0, 1, 1. They're the same or different values. Explain. The key is explain. Make sure I see that, okay? Would 2 bits be enough to assign a unique binary number to each vowel in the English language? Interesting. So if you had only 2 bits, meaning 2 places, not 2 bytes, but 2 bits, the first 2 places. Is that enough to assign a unique binary number to each vowel in the English language? A, E, I, O, and U. Is it possible? Find out. How many bits would you need if you wanted to count up to the decimal number 1,000? So how many bits, how many places to get up to the decimal number 1,000? None of these are easy answers. You do have to work with your partner to figure it out. You may work in pairs, but you're each going to hand in your own work after today. Best of luck, and thank you for watching.